I have some really exciting stuff to talk about. You know, I'm a planetary scientist, and so we study the planets, and we know Earth's place in the solar system. But there's a number of really important subtleties that are going on that we need to understand. And indeed, we are so lucky to have Venus and Mars in our solar system so that we can study them, understand their evolution, and that indeed helps us understand the evolution of the Earth. So what we do know, of course, is the planets are arrayed in certain distances from the sun, and that means the enormous amount of energy that the sun provides us becomes less and less as you're further away. So Venus, which is closer to the sun than the Earth, we know that it gets about 2,800 watts per square meter of sunlight. And of course, that input is what really is important, and what we do with that input in each of these planets is important to understand, and that really is where the atmosphere comes in. Because as we see, the atmosphere on Venus, which is dominated by carbon dioxide, enormous greenhouse potential, has gone to the point where it is in a runaway greenhouse effect, causing the surface temperature of the planet to be over 860 degrees Fahrenheit. Now, that's hot enough to melt lead. Now, without the atmosphere, it would only be 64 degrees Fahrenheit, you know, like a nice day here on Earth, so to speak. But indeed, the atmospheric composition has an enormous amount to do with the heating of the planet. Here on Earth, we receive about half that energy that Venus gets, about 1,400 watts per square meter. Now, without an atmosphere, we would have about 1 degree. You know, everything would be freezing, you know. It wouldn't be the water that we see today in liquid form be able to be maintained on the surface of this planet. But our greenhouse gases really are very important, and it does warm our planet. And as the heat from the sun warms our oceans, and the water vapor continues, that provides a greenhouse gas, but it is not the only greenhouse gas. Indeed, the CO2, which contributes to that warming, adds to the heat that then allows water vapor to increase. Again, those things are all interconnected, and so we must understand what that interconnection is all about. Mars, on the other hand, is half the energy received by the sun that the Earth gets, only about 600 watts per meter. And although it has a very thin atmosphere, even that carbon dioxide, very thin atmosphere, producing a little greenhouse effect on Mars, heats it maybe 8 or 9 degrees Fahrenheit. So what we want to know then is, let's look at the evolution of these planets. What's really been spectacular in terms of the science that we've uncovered by looking at Venus and the history of Venus is that Venus really was a blue planet. We believe it contained an enormous amount of water, had oceans, and maintained those oceans for several billion years. And it's only been within the last 800 million years or so that the greenhouse gases then took control, evaporated the oceans, and caused the runaway greenhouse gas environment that we see on Venus today. We also notice from orbit that Venus is still very active. It generates an enormous amount of carbon dioxide and sulfur dioxide and water vapor coming from the existing volcanoes that are there on Venus today. And that, of course, contributes to the greenhouse effect. This is really important to study because it enables us to think about what is the evolution of the Earth. And so what we're finding today on Earth is the beautiful array of volcanoes, just like what's on Venus. These volcanoes, the three basic types of volcanic activity is going on. Now, even though our atmosphere is dominated by nitrogen, and these do produce CO2, as Gavin mentioned, the CO2 production that humans produce, these pale in comparison. But it's exciting to understand the evolution of this planet because of its plate tectonics. St. Vincent, for instance, which is in the Caribbean, it has one plate moving under another. And this subduction indeed heats and melts the crust, wrings out the water and the volatiles, and it comes out in these beautiful displays of volcanoes. We also see the Reunion Island hotspots. These are hotspots sort of inside these plates that where magma pokes out. Reunion Island is east of Africa. And indeed, it is also generating beautiful volcanic gases and melted rock. And then finally, Iceland, which has been going on now for a while, is right at a spreading zone. So it's at an area where the plates are moving apart, and then magma has the opportunity to come up. So these are the three basic types of volcanic activity going on in Earth. And they're beautiful to see and beautiful to study. And we must study those to really understand the origin of life and the change of climates that occur over time, because they point us to that important plate tectonics. So here is a high-level overview, as seen from a planetary science perspective, from the beginning of our solar system 4.5 billion years ago, of how the Earth could have been habitable over time. In other words, where we obtain our oxygen atmosphere and have an environment where life can become more complex as we know it today. And as you can see, this habitability index seems to indicate that after the Earth was formed, it happened to be in the right place with the right amount of material like water, also the right organic compounds and material, where there's something happened, a spark occurred, and life began. And over time, we were sheltered in a way that allowed life to be able to really take hold and then change the actual composition of the atmosphere. So as you see in the bottom, our atmosphere indeed is dominated by nitrogen. In the past, we had a significant amount of carbon dioxide. That turned out to be really important because the sun wasn't giving out as much energy, and so we needed that CO2 greenhouse effect to keep the Earth warm and to keep the water in a liquid, gas, and also frozen phase, and let the Earth evolve over time. And then, of course, with the onset of plants and photosynthesis processes really kicked in, creating a much more complex life here on Earth. But there's more to the story than just looking at the atmospheric compositions and how it changes. We now know that as we orbit the sun, the gravity from the planets that we pass by, or they pass by us, depending on where they are in their orbit, actually affects our own orbit. And because that orbit distance from the sun is that initial input of light, we must try to understand how that varies over time. And about 100 years ago, an astronomer by the name of Dr. Milankovitch created that basic knowledge that we call now the 3 Milankovitch cycles. The first one is the eccentricity of our orbit. How circular is it? And we find out over time the tugs and pulls by the planets, and in particular Jupiter, which has 300 times the mass of our own Earth, pulling and tugging on the Earth, has indeed changes the ellipticity of our orbit, making it more egg-shaped, if you will, over time. Now that has a certain cycle. It's about 100,000 years. There's another beat period on top of that where it can grow even more or less, which is at about 400,000 years. So there's important cycles that go on. And because the rest of the planets are moving in predictable ways around the sun, we can really map out how our orbit changes over time. And so right now, our orbit is very close to being circular. But it can have an ellipticity of about 0.06. Now, another cycle that we have is called the precession. And this is where, because we are in an elliptical orbit, we want to know where that closest approach to the sun is, what we call perihelion. And when is the season that we see that? Now, right now, the season where we are closest to the sun here in the northern hemisphere occurred around January 4th. And that is, of course, the northern hemisphere winter. And so that's where we receive more light from the sun because we are several million miles closer to the sun than when we are half a year later, when it's southern hemisphere winter. Okay, and so that cycle is shifts over time, and that is that shift of the time of the perihelion on a cycle of about 26,000 years, and that's called precession. So our orbit precesses around the sun. That elliptical shape does not only change, but then slides over time. And then the third really important cycle, of course, is indeed our tilt. Now, everyone knows our axis points to the North Star, but that's not always the case. Over time, the axis changes ever so slightly from about 22 degrees to about 24 degrees. And right now we're at 23.5 degrees. And so these are the three major cycles. And then there's one other really important factor we must talk about, and that is the effect of our moon. It turns out our moon keeps the Earth uncommonly habitable. It stabilizes that rotational axis. In other words, that 23.5 degrees, which changes only by a few, is because the moon is keeping us in that position. For other planets, it's very different. The moon also stabilizes and causes lunar tides and slows our rotation rate, so that in a 24-hour period with the tides, life has learned to live and indeed survive on these type of changes that the moon produces in our environment. Just as a comparison, what about Mars? Well, Mars has two really small moons, nothing like our own moon, which is a significant mass. In fact, those moons are only 20 kilometers or so in size and are more like asteroid size or small body size. And so they don't really provide that stability of the axis. So as we see here, the obliquity, okay, or how that angle of our rotational axis changes over time. For Earth, it's just that few degrees, as you see, but Mars changes from 15 degrees, in other words, nearly with its rotational axis perpendicular to the orbit plane, all the way over to 45 degrees, nearly laying down. And so this is really a huge change, and it's because it doesn't have a moon to keep that rotational axis as steady as our own moon does to us. Well, we can look at these three cycles, the eccentricity, the precession, and the tilt over time, and we then can calculate indeed the change in the energy that we receive from the sun based on these perturbations, not only of our orbit, but of our rotational axis. And we see there's a natural swing. These are the three added Milankovitch cycles. And that change will occur with a temperature difference of nearly 11 degrees Fahrenheit. Now, these are slow changes, but indeed they have enormous effects on the past history of this Earth and the development of humans as complex beings and many different cultures. And so Here's an example of what the Earth, perhaps the vegetation on Earth looked like 122,000 years ago, compared to this mini ice age that we went through because of the Milankovitch cycle 5,000 years before present. And so indeed, this is a really exciting way to look at our history and to look at how climate evolves and create a baseline for which then we can understand the effects of the climate that humans are producing by adding these greenhouse gases. And the key one, of course, is indeed CO2. I want to draw your attention to some exciting changes. You know, I'm a history buff, and so indeed, not only planetary history of 4.5 billion years, but I enjoy history here on Earth too, you know. And so if we look at Africa, as a matter of fact, only about 8,000 years ago, when the ice was down in the Canada and New York area and beginning to melt and creating the Great Lakes, and in Europe, it was in England and down into France, because of the weather patterns, it turns out the Sahara Desert was really what we would call, you know, perhaps a Garden of Eden in the sense that it was a green Sahara. It had an enormous number of rivers and lakes. Now, one of the exciting things that NASA's been doing, of course, is as it flies over Africa with a variety of instruments, with ground-penetrating radars, we have uncovered some of these ancient river valleys that are now covered in sand. We have found the old, indeed, lakes that were there, and old cities where prehistoric individuals lived and worked in a community over time before history was really written down. In addition to that, what's really exciting is the writing of the time wasn't the written record as much as it was the visual record of events that were occurring. Now, these are called the Tassili frescoes. They have been seen, photographed for several decades now. You can go into the Sahara, and these aren't cave paintings, as we know Neolithic humans did, but these are on the walls of mountains and sides of cliff, and they depict village life, you know, drawing water, having a wedding, and then herding cattle. And so, indeed, these are tremendously exciting elements of our past. So what's happened over time through the natural cycle of our own Earth that we must understand to then feather out what's happening with human changes induced in our climate is indeed the past has changed in Africa significantly. So over the last 5,000 years, these people moved to the coasts into Central Africa and then into Egypt, where they established the fantastic Egyptian culture. So these are just some of the few things that are occurring that indeed climate change happens all the time. And this is what's really important. It's not about the change. From a planetary perspective, climate changes are part of our history as it is the planet's. It's the rate of change. And as Gavin mentioned, that right now is so measurable and so different than expected. We now enter a new regime of understanding. So the Earth is warming faster than its natural cycles. Now, the sun, even though as it evolves, we know will increase in intensity, but that is so extremely small. Even on tens of thousands of years, it's really negligible. But we're seeing significant sea level rise. We're seeing ocean temperatures, surface temperatures, and atmospheric temperatures increase. You know, as Gavin mentioned, the overall average temperature, this is what climate is really all about, is looking at averages over long periods of time, has indicated an increase in temperature of about 2 degrees. Now, indeed, the Milankovitch cycles would be telling us that in about 1,000 to 2,000 years, we should be going down in temperature because of the downward cycle, our orbit becoming more elliptical. We're getting further away from the sun. And that's not the trend we're seeing. In fact, of course, that increased heat melts our glaciers and indeed melts the Arctic ice. So greenhouse gases are the culprit. You know, the CO2 heats up our water, creates water vapor. You know, the tundra has a lot of methane, gets released. And indeed, this is a cycle that we're just now being able to understand. And we need to, because we can see we don't want to become more Venus-like, you know, so we need to be able to really appreciate how we take care of this globe over time. So in summary, you know, Earth's orbit changes on a time scale due to gravitational forces from the other bodies of tens of thousands of years, and they create the Milankovitch cycles. Fortunately, we've had the moon that helped mitigate many of these huge changes that might have occurred by keeping our rotational axis near 22 to 24 degrees. But that still produces some small changes in our climate that we now understand and predict. In fact, the climate change, as I mentioned, is occurring at a larger rate than what we would predict from the climate cycles that Milankovitch uncovered in his groundbreaking understanding more than 100 years ago. So for more information, please go to climate.nasa.gov.